So in our last lesson, we finally proved the fundamental theorem of arithmetic for the Gaussian integers. And we classified how all the Gaussian primes are as a consequence of that. And today we're going to go ahead and build upon that, and we're going to start off with a bang and see our second proof of Fermat's sum of squares theorem. But now in the context of the Gaussian integers. And so this is the proof that Richard Dedekind discovered in 1894. And as we will see, this is much simpler than Euler's original argument, and it shows that the property of those primes, which are sum of two squares, is really a consequence of the structure of the Gaussian integers. Similar results hold true for the other cases that Euler studied, the primes of the form x squared plus 2y squared, the primes of the form x squared plus 3y squared. And so those are situations where you will have to look at the integers, but then you want to adjoin the square root of -2 and the square root of -3, and then similarly to how we proceeded in our course the past week, we can go ahead and prove analogous results that there is a division theorem, that there is a fundamental theorem of arithmetic, and so we can do the same exact setup and prove those two results in that context. And this is, as I've mentioned in the past, what led in many ways to the foundations of abstract algebra. And 1894, Richard Dedekind proved this result, and less than 20 years later, Emmy Noether had generalized these notions to what are known as commutative rings today. And so let's go ahead and get started. So we're going to go ahead and prove Fermat's sum of two squares theorem. And we have already done the heavy lifting for this, and as we will see, the proof is much simpler. So let's go ahead and show the forward direction. So for this, we have that p is equal to a squared plus b squared if and only if p is congruent to 1 mod 4. But now, that is the contrapositive of proposition 1.23.1. And so this is the contrapositive of proposition 1.23.1. And so we're done with one direction. So let's go ahead and prove the backwards direction. So let us go ahead and take p. So p is congruent to 1 mod 4. So by theorem 1.23.3, we have that p is not a Gaussian prime, since it is not a Gaussian prime, we can find two Gaussian integers that are non-units in z adjoin I, such that p is equal to the product of those two Gaussian integers. So to that end, let's go ahead and let a, b, so then there exists a, b, c, d integers such that p is equal to a plus bi times c plus di, and since they are not units, we also have that the norm of a plus bi and the norm of c plus di, that these are greater than 1. So we have this condition. If we go ahead and now take norms of both sides here, say taking norms gives that p squared is equal to the norm of p, which is equal to the norm by the multiplicativity of the norm. This is the norm of a plus bi times the norm of c plus di. But this here is equal to a squared plus b squared for the norm of a plus bi. And the norm of c plus di is equal to c squared plus d squared. So we have our product of norms. But now all of this is back in the realm of the natural numbers. We have that p has to divide this here. And so in particular, since these are all natural numbers, so c squared, a squared plus b squared, plus d squared is an equation in the natural numbers. We have that p divides a squared plus b squared, or p divides c squared plus d squared. But now we have that p divides a squared plus b squared, p divides c squared plus d squared. This is an OR, but it's actually an AND, because we know that the norm of a plus bi and the norm of c plus di, these are both greater than 1, and so a squared plus b squared and c squared plus d squared are both greater than 1. And now we have p squared divides these two quantities, and so p must be equal to a squared plus b squared, which is equal to c squared plus d squared. And so since a squared plus b squared and c squared plus d squared is not equal to 1, we conclude that p is equal to a squared plus b squared and c squared plus d squared. And that concludes our proof, because now we have written that p is actually a sum of squares. And this is the beauty of this argument, is that gone is the descent lemma and having to do infinite descent to prove this. Now we just get it as a consequence of the multiplicativity of the norm and the fact that since primes of the form that are primes congruent to 1 mod 4 are not Gaussian primes, then we end up getting this equation here upon applying that definition. And now we are done. We have proven Fermat sum of squares. But working over the Gaussian integers, we can go one step further than what we could do with the tools that Euler had at his disposal. So given a prime, say 5, we know 5 is 2 squared plus 1. We know 13 is equal to 3 squared plus 2 squared. Given some prime equal to a squared plus b squared, can we write it in another way as a sum of squares? How many different ways can we write a given prime as a sum of squares? Because with 5 and 13, we can see that that's the only way up to order. But what if we had an arbitrary prime? How do we go about verifying that? Euler's proof just showed that a prime congruent to 1 mod 4 is a sum of squares, but it never said anything to the effect of how many ways we can write a prime that's congruent to 1 mod 4 as a sum of squares. And so that's our next statement, which tells us that there's only one way up to order that we can write a prime congruent to 1 mod 4 as a sum of two squares. Okay, so let's go ahead and prove this. So proof. So let p equal a squared plus b squared equals c squared plus d squared for a, b, c, and d integers. And so now we have these two ways of writing p. And what we are going to see is that they are the same up to order. And so the way we're going to go about this is by realizing that if we have that p can be written as a sum of squares, over the Gaussian integers we have a factorization for p. So specifically, we have that p is equal to a plus bi times a minus bi, which is equal to c plus di and c minus di. So we have these two factorizations here. The next thing is if we take norms, just observe that the norm of A plus or minus BI and the norm of C plus or minus DI, this is equal to P, since the norms are going to be A squared plus B squared and C squared plus D squared respectively. Now we apply lemma 120.6, which tells us that if the norm is prime in the integers, then the norm of Z is prime as a Gaussian integer. So by lemma 1.20.6, we have that A plus or minus BI and C plus or minus DI are Gaussian primes. But now we have over here two different prime factorizations for P, or so they look. But we know by the fundamental theorem of arithmetic for the Gaussian integers that these two factorizations are the same up to unit and order. So by the fundamental theorem of arithmetic for the Gaussian integers, we have that A plus BI is equal to some unit times C plus DI, or A plus BI is equal to a unit times C minus DI. And so we have these two possibilities, since we know that they are the same, up to unit and order. And now we're going to utilize a exercise that you'll be doing for homework. And so specifically by under these assumptions, you will show in 13.6 number 7 that this here, these conditions, it implies that A squared is equal to C squared and B squared is equal to D squared, or the second case, which is A squared is equal to D squared and B squared is equal to C squared. And that finishes the proof, because now what we have is that up to order, we have that in this case A and C are the same, A squared and C squared are the same, B squared and D squared are the same, so it's the same way of writing it, or we change the ordering. So A squared is D squared and B squared is C squared. And so now we have that uniqueness that under Euler's method of attack we were unable to get. And so that's one more aspect as to why working over the Gaussian integers gives us this much more natural and robust way of working on questions like these that we could not do with the techniques that were available to Euler in the 1700s. But keep in mind, now we're at the late 1800s, and this brings us to Fermat's last theorem. Because in order for Dedekind to get to this result, many of the ideas that led him down this path of making this realization in terms of factoring in terms of primes over the Gaussian integers was by what had been done in the literature up to that point in trying to solve Fermat's last theorem. And so to close our term, we're going to go into a deep dive through the history of Fermat's last theorem and prove what is known as Sophie-Germain's theorem for auxiliary primes. And so as a reminder, our favorite writer of marginal notes, it is impossible to separate a cube into two cubes, or a fourth power into two fourth powers, or in general, any power higher than the second into two like powers. I have discovered a marvelous proof of this, which this margin is too narrow to contain. And so we are going to go through it as part of our course in the next couple of weeks and prove the n equals to 4 case of Fermat's theorem, as well as see a special case, as I mentioned with Sophie Germain's work, of Fermat's theorem. So we're going to be getting to see this in action. And to close out the term, I will go through a rough sketch of the ideas that followed throughout the 1900s that eventually did lead to the proof in 1994 of Fermat's theorem. But to do so, we need to venture back to the statement that started all of this, namely Diophantus's Arithmetica. And so, if you recall, when we first talked about Fermat's theorem, I mentioned that the marginal note that Fermat wrote down was next to a specific statement of Diophantus that pertained to what the Pythagorean triples are. And so in the homework, in the exam, you had the opportunity to prove that a classification of all the Pythagorean triples. But that used geometry. You used the fact that x squared plus y squared is equal to 1, that's the unit circle, and you found lines. But that was not a method of proof that Diophantus had at his disposal. Although we take that for granted today, that is a very recent discovery. It was with the work of Descartes in La Géométrie that mathematicians began to realize that algebra and geometry can be worked at simultaneously, and this gave birth to calculus in the years that followed. In the time of Diophantus, thinking about x squared plus y squared is equal to 1, that was not a circle, but a polynomial equation. And so he worked at solving polynomial equations, and so algebra was completely disjoint from geometry. And so the proof that you saw in the exam is a modern argument of what Diophantus originally did. And so we are going to go ahead and prove Diophantus' original theorem that classified what the Pythagorean triples are. And so to set standardized terminology, we're going to say that a triple, ABC, of natural numbers is a Pythagorean triple if we have that a squared plus b squared is equal to c squared. And we are going to call a Pythagorean triple primitive if a, b, and c are all relatively prime natural numbers. And so the first statement is that if we have z and n natural numbers such that z to the n is equal to d times e, where d and e are relatively prime natural numbers, then there exists some natural numbers x and y such that d is equal to x to the n and e is equal to y to the n. So let us go ahead and prove this result. So let us go ahead and take z to have the following prime factorization. So this will be the prime factorization from 1 through r, p sub j to the aj, where each p sub j is a distinct prime, then z to the n is going to just be the same product with now everything raised to the n. So we have p sub j, and then we have n times a sub j. So we have this here. But this is equal to d times e. So in particular, each p sub j to the n times a sub j divides d and e. Since d and e are relatively prime, we have that p sub j to the n times a sub j So we have that either p sub j to the n a sub j divides d, or p sub j to the n a sub j divides e. So these are the two possibilities we have. Relabeling if necessary. We may assume that d is the product from j is equal to 1 through some m, and now we have p to the sub j to the n a sub j, and e is the product where now we're starting at m plus 1 and then going through r. So we're just relabeling, so we have these prime factorizations in this way. But now we are done, because now we can go ahead and take x. So we take x to be the product from 1 through m of the p sub j's to the a sub j's, and y to be the product from m plus 1 to r of the p sub j's, a sub j's. So letting this gives that x to the n is going to be d, and y to the n is going to be e, which is what we wanted to prove. And so now we have shown that existence of x and y, so that d and e are both perfect nth powers. And so that's the key takeaway here. And now we can go ahead and prove Diophantus's classification. And so here is the Pythagorean triple theorem. And so what it says is, if we have natural numbers a, b, and c, then a, b, c is a primitive Pythagorean triple if and only if there exists relatively prime numbers p and q of opposite parity, such that p is greater than q, and the following equations hold after positively interchanging the a's and b. So a is equal to 2 times pq, b is equal to p squared minus q squared, and c is equal to p squared plus q squared. So we're going to prove the backwards direction first. So if we start off by assuming this here, then we want to show that that's a primitive Pythagorean triple. So observe that if we take a squared plus b squared, that is going to be 4p times q squared here, and then we're going to have a squaring of the b squared, which is going to be p squared minus q squared, quantity squared, but that's going to give us a p to the fourth minus 2p squared q squared plus q to the fourth. But then this here adds with this as a positive 2. And so we have that this here will just be p squared plus q squared quantity squared, which is our c squared. So that checks out. So now let d divide let d be the GCD of a, b, and c. Then since b and c are odd, and so this is coming from the opposite parity. Since p and q are of opposite parity, we know that p squared minus q squared has to be odd, and similarly with p squared plus q squared, since odd and even, adding those will always give us an odd quantity back. And so since b and c are odd, we have that d is odd. since D divides A, which is 2 times P times Q, we have that D divides P times Q. But we also know that P and Q are relatively prime. So by assumption, P and Q are relatively prime, and so Euclid's lemma implies that D divides P or D divides Q. So we have these two possibilities. So let us go ahead and suppose that D divides Q. If D divides Q, then we end up getting, since B plus Q squared is equal to P squared, so this implies, via the linear combination lemma, that D, since D also divides B by assumption of B being the GCD, we have that D divides P, but P and Q are relatively prime. But now we have that D divides both P and Q, and thus D is equal to 1. And a similar argument holds for D divides Q, which concludes, for D divides P, which concludes this direction. Because of course if D divides P, we can do the same exact argument, where we could look at B minus P squared equals negative Q squared. Linear combination lemma will imply D divides Q, and so we get the result we want. So that takes care of the backwards direction. Let us go ahead and now show the forward direction. So we're going to start off by claiming that C is odd. So let A, B, C be a primitive Pythagorean triple. We claim that C is odd. So towards a contradiction, suppose that C is even. Then A squared plus B squared has to be congruent to 0 mod 4. Because if C were even, then C squared is going to be divisible by 4. And so we have A squared plus B squared is congruent to 0 mod 4. But this equation only holds. Now this equation only holds if A and B, A or B is even. Because if A and B are odd, we're going to have A squared is 1 and B squared is 1, and that's just going to give us congruent to 2 mod 4. Since A squared is congruent to, let me write this, since n squared is congruent to 1 mod 4, if n is odd. But if this is the case, but this is a contradiction. The GCD of A and C being equal to 1, since we started off by assuming that C was even, but now A has to be even. And so that takes care of that part of the statement. So we may assume that C is odd. Moreover, one of A or B has to be even. One of A or B must be even. With all loss of generality, we assume that A is even and B is odd. Since they're relatively prime, we know that B must be odd. Then, if we look at the equation a squared plus b squared equals c squared, we can get a difference of squares. We have a squared is equal to c squared minus b squared, which is c minus b times c plus b. But now, since a is even and c and b are both going to be odd, we have that c minus b and c plus b are going to be even. So then, c plus or minus b is even. And so we have this here. And now we're going to go ahead and make a substitution. So we're going to go ahead and, not a substitution, we're going to make a definition. So we're going to go ahead, since we know that a is even, we're going to set a to be equal to 2 times AU. And similarly, we're going to take C plus B to be 2V. And C minus B to be a 2W. For some UVW in the natural numbers. So notice that we can take them to be in the natural numbers, since the assumption that we have a squared plus b squared equals c squared tells us that c is greater than b. So c minus b is a positive integer, so it's a natural number. So we have this here. Now what we are going to do is come back to this equation and substitute in for a squared and for c minus b and c plus b. So consequently, we have that a squared, which is 4u squared, is equal to c minus b times c plus b, which is going to be 4 VW, which implies that u squared is equal to v times w. So we claim that v and w are relatively prime. So let us go ahead and take d to be the GCD of v and w. And now we're going to come up to these two equations. We have c plus b equals 2v and c minus b equals 2w. And so if we add these together, we get the following. So we add c plus b to c minus b. That's just going to give us a 2c. So we have a 2c equals 2v plus 2w. And so we have a 2v plus w. And by linear combination lemma, d now divides 2c upon canceling. So we can also cancel off over here. We divide by 2. And we have c is equal to v plus w. And that allows us to deduce that d divides c. So similarly, now we are going to subtract the equations. So we're going to take this here and subtract it from this equation. So doing so is going to give us a 2b is equal to 2, and then we are going to have v minus w, which tells us that b is equal to v minus w, and once more by linear combination lemma, d now divides b. But we know that b and c are relatively prime. And so that tells us that d must be 1. But now we are in the content of lemma 1 to 4.1. We have a square is equal to a product of two quantities that are relatively prime, so those quantities must be perfect squares themselves. So by lemma 1 to 4.1, there exists natural numbers, and so let's go ahead and call those natural numbers p and q. Such that v is equal to p squared and w is equal to q squared. So in particular, we see that c is equal to v plus w. So we have c is equal to p squared plus q squared, and b, which is equal to v minus w, is going to be p squared minus q squared. And so that establishes these two quantities right here. But we also know that a is equal to 2 times u, and u squared is equal to v times w. So moreover, we have a squared is equal to 4u squared, which is then in turn equal to 4vw, which is p squared, 4p squared, q squared, which implies that a is equal to 2 times p times q. And now we have our quantity. And so we have our a. And so we have all these three. And we know that the p and q are of opposite parity. So note that p and q are of opposite parity. Since c is odd. And we know that c is v plus w. So if they had the same parity, so if they were both odd, then we will have that c is even. And if they were even, then that would be a contradiction on the relatively primeness. And so we have completed the proof. We have proven the Pythagorean triple theorem. So the last thing that is implicit in the argument, and to actually erase here, since we did not mention it. So note that B is equal to V minus W, which is then P squared minus Q squared. And we know that B is a natural number, so this is greater than 0. And so that implies that P minus Q is positive, which implies that P is greater than Q. And so now we are officially done. We have proven the Pythagorean triple theorem. And so this is going to get us one step closer, as we will see in our next lesson, to prove Fermat's last theorem for the n equals to 4 case. Since it was this theorem precisely that set Fermat to consider a generalization of this statement by considering what happens if we have perfect cubes, perfect fourth powers, if these equations held. And so far, the statements that we have seen by Fermat, none of those he has proven. But there is one statement that Fermat did prove, and that is the right triangle theorem. And using the right triangle theorem, we can deduce Fermat's last theorem in the n equals to 4 case. So in our next lesson, we are going to use the right triangle theorem of Fermat to prove the Fermat's last theorem in the n equals to 4 case, and we will also go over Euler's original proof for the n equals to 4 case. But to discuss the right triangle theorem, which is the only known proof that Fermat ever wrote down, by the way, we need to talk about infinite descent. This was a technique that Euler used in his proof of Fermat's sum of squares, and this is a technique that is credited to Fermat, as Edwards, who wrote a history on Fermat's last theorem, to quote him, Fermat invented the method of infinite descent, and it was an invention of which he was extremely proud. In a long letter written towards the end of his life, he summarized his discoveries in number theory, and he stated very definitely that all of his proofs used this method. Briefly put, the method proves that certain properties or relations are impossible for natural numbers by proving that if they held for any numbers, they would hold for some smaller numbers. Then by the same argument, they would hold for some numbers that were smaller still, and so forth ad infinitum, which is impossible because a sequence of natural numbers cannot decrease indefinitely. But that is the strategy that we saw in proving the Euler descent lemma. And so if we recall the proof of this statement, in the proof of Euler's descent lemma, the way he went about it was by constructing this sequence of decreasing natural numbers. And that was where he got his contradiction. We bypassed that argument by writing everything in terms of a set S and applying the ordering principle so that we started with the least element. But if we had done this without choosing the least element, then the argument that we did in the Euler's descent lemma would eventually get us to a quantity that satisfies the same property but smaller still, and then we can just continue this process ad infinitum to get a contradiction. And so Fermat did use this method in proving the right triangle theorem. But now, one thing to note with the right triangle theorem is that while he proved it, his proof, and the only proof that he ever wrote down that survived, is by our standards not a rigorous proof. And so let's talk about the right triangle theorem to finish off today's lesson. What it says is that the area of a right triangle with integer sides cannot be a perfect square. And here is Fermat's original proof. This is a translation from Latin of what Fermat wrote down in the margin of his copy of the Alphantis' Arithmetica. And right off the bat, he actually does assume something that requires quite a bit of proof. We are not proving Fermat's right triangle theorem, at least in the lesson, but for homework, you will be given a guided proof of Fermat's right triangle theorem. And I highly encourage you, as you work through that question that guides you to proving this statement, compare notes with Fermat's original proof. Because what you're going to find out is that there are many gaps throughout this. So he starts off by saying if the area of a right triangle were a square, there would exist two biquadrates, and so this just means two perfect fourth powers, the difference of which would be a square number. And that's something that needs to be shown, and Fermat did not show it. And so you'll be tasked as part of your guided homework in proving this statement. And even at the very end of the proof, he does his classic, the margin has run out and I cannot fill in the details. And so we see at this stage over here in the proof that he says, this is however impossible because there cannot be an infinite series of numbers smaller than any given integer we please. The margin is too small to enable me to give the proof completely and with all detail. And that is the only proof that has survived Fermat. And so you'll be tasked with going through proving Fermat's right triangle theorem as part of your assignment, and please read through this proof as you work through that assignment. And so in the next lesson, we are going to go ahead, assume the right triangle theorem, and see how the n equals 4 case of Fermat's theorem follows easily from it. And for that reason, Fermat is credited with having proven the n equals 4 case of Fermat's theorem.